Welcome back. This is the fourth and final video of Unit 3, and it is going to cover reinforcement learning. So reinforcement learning, once again, is a third alternative. It's not supervised learning, it's not unsupervised learning, but we're going to explain it here and now and talk about it because this is one of the coolest parts of machine learning and is actually going to be the focal point for our final project in this class. So it's important that we cover it and understand how and why it works. So let's get started. So here's just a quick introduction. And again, this is just showing that machine learning as a whole is comprised of supervised learning and unsupervised learning. Nobody really wants to throw reinforcement learning into these two categories, one of these two categories, because it doesn't have really the same characteristics as the other two. So in reinforcement learning, we don't have a supervisor, only reward. So we don't have that output that's telling us this is a positive example or a negative example. Furthermore, the feedback is delayed. We might have to make some choices in the here and now, and we're not going to understand if those were good or bad choices later on. Next, time really matters in reinforcement learning applications. Well, most of reinforcement learning applications. So we're going to have to consider time as well as the simple results or output of our algorithm. And finally, the agent's actions affect the subsequent data it receives. So depending on what our algorithm does, the environment or the input space is going to change. So that is definitely different than our supervised or unsupervised learning examples where our input data was very static. It was set beforehand, and then we applied our algorithm to it. So some examples of reinforcement learning would to be defeat the world champion at backgammon or chess, or to make an investment portfolio, control a power station, maybe make a robot walk, or play an Atari game. So these are some very cool applications of machine learning. They're what come up in articles more often than the other machine learning techniques. It's also one of the newer machine learning approaches and has some of the coolest applications, I think, in my opinion. In Unit 4, when we talk about neural networks and deep learning, we are going to continue talking about reinforcement learning because it is used in conjunction with deep learning networks a lot of the time. But let's keep diving into the specifics. So the goal of reinforcement learning is to learn the best policy, that is, the sequence of actions that maximize our total reward. So we'll go in, we'll define some of these words like policy or agent in a bit here. But for now, it's important to understand that the overarching approach is to not make the best choice or action at each individual step. It's to make the best policy, which is going to be a sequence of actions taken by the agent that maximizes the total reward. So, for example, if we're playing the game of chess, we don't necessarily want to just make a good move at every single instant. We want to win the game. So if we build a machine that learns to play chess, in this case, we cannot use a supervised learner for two reasons. First, it would be very costly to have a teacher that will take us through many games and indicate the best move for each position and situation. And then second, in many cases, there is no such thing as the best move, as I just mentioned. So the goodness of a move depends on the moves that follow. So that's very different than other machine learning applications we've looked at. A single move does not count. A sequence of moves is good if after playing them, we win the game. So winning the game is going to be our reward here. And the only feedback is at the end of the game when we win or lose the game. So our algorithm is going to have to make choices not knowing or not getting immediate feedback on those choices. Another example would be a robot in a maze. So the robot can move in one of 4 compass directions and should make a sequence of movements to reach the exit. So as long as the robot is in the maze, there is no feedback, and the robot tries many moves until it reaches the exit, and only then does it get a reward. So in this case, there is no opponent, but we can have a preference for shorter trajectories, implying that in this case, we play against time, so we have time considerations in this example as well. So we had a lot of terms in those kind of examples and definitions, so let's help with that and define some of our elements of reinforcement learning and actually define some of these terms. So in reinforcement learning, we have what's called the agent. And the agent is simply going to be the decision maker which performs the learning. So the agent, again, is the algorithm that we are trying to teach. And the agent interacts with an environment, that is the area, space, or game that the agent is in. For example, in chess, the game player would be the agent, and then the board is the environment. And specifically, the board will have what's called a state. So that is the current environment. And the environment is in a certain state that is one of a set of possible states. So, for example, the position of the robot in our maze or the current position of every piece on the chessboard would be good examples of state. Interpreting that state, our agent can then take what's called an action. So actions are possible moves by the agents, such as a legal move in chess or the possible directions without hitting the wall for our robot in the maze. Based off that action, our agent is going to get a reward. So this is feedback on our sequence of actions. Generally, this is only received when the completed sequence is carried out. So, for example, we get +1 if we won the chess game, -1 if we lost. So we want to maximize our reward, so we want to win as many games as possible. And the learning agent learns the best sequence of actions to solve a problem, where best is going to be quantified as the sequence of actions that has the maximum cumulative reward. So it's really going to be dependent in these scenarios how we define our reward. Some other terms that you might want to know are episode or trial, and these are going to be the sequence of actions from start to the terminal state. So we have some initial state that begins our episode, and then after the episode, all our sequence of actions has been undertaken. And then finally, policy, and that's going to define the action to be taken by the agent in any given state. And policy is really what we care about. It's not each individual action, it's how we respond to the environment in any given state, because that is going to define our sequence of actions, which helps us reach our goal. So this is the general setup. These are the elements of reinforcement learning. Let's dive into the environment in a little bit more detail. So the environment can really have two different scenarios. We can have fully observable environments. So this is going to be when the agent directly observes the environment state. And this is known as the Markov decision process, or MDP. And fully observable environments are when the agent has complete access, complete knowledge of the environment that it's in. So maybe it knows all of the rules of the game that it's playing, or it understands the complete map of the maze that it's trying to solve. In other scenarios, you're going to have partially observable environments, and the agent indirectly observes the environment state. So, for example, maybe we have a robot that's trying to navigate through our maze, but the robot only has a camera and doesn't know its absolute location. So the environment or the state is going to be dependent on the location of the robot, but the robot doesn't understand that. It doesn't know its exact location. So this is going to be partially observable. So the agent state does not equal the environment state. In this is known as a partially observable Markov decision process, or POMDP. And once again, the agent must construct its own state representation because it only has partial information here. And this state representation that the agent creates is going to be based on the complete history of observations that it's made, and as well as beliefs of the environment state. So it's going to try to make future predictions off of prior information because it doesn't know the entire environment. But we'll take a look at some of these a little bit later on. But for now, let's explain the agent in a little bit more detail. So the agent may contain one or more of the following components. The first component being the policy. And the policy is simply going to be the agent's behavior function. So this would be a map from state to action. So given a certain state, maybe the position of chess pieces on the board, we're going to perform the particular action or this move. The next component would be a value function. So how good is each state and or action? So these value functions are going to take into account future rewards. So we're going to try to make a prediction of future rewards and move in the direction or take the action that maximizes our value. And ultimately, this is going to help us develop a policy. Finally, we might have a model in our agent, and this is going to be the agent's representation of the environment. So a model is going to help us because we can predict what the environment will do next. So you see both a value function and a model are going to help our agent form predictions. In the last slide, we talked about a partially observable environment and how an agent would create its own state representation based off beliefs on its environment state. A value function and a model are going to help that agent create these beliefs. So once again, an agent doesn't have to have all of these components. It certainly doesn't need to have a model. However, these are different aspects of an agent that may help it learn or generalize to new scenarios. So let's use an example to go over this, and we're going to continue using our maze example. So here we have the environment. We have an initial state, the start location, and we have a final state or a goal that we're trying to reach. So we can take any sequence of actions to get there. However, in this scenario, we're going to have some rewards, and we're actually going to get -1 per time step. So we want to take the fewest number of steps possible. Our available actions are going to be to go north, east, south, or west. So we're confined to 4 distinct actions. And the state in this case is going to be the agent's location in our maze. So if we're using policy, this is what a policy might look like. And each little box, an arrow is going to represent the policy for each individual state. So if you look at this upper right image, if our agent was in the very bottom left box, you'd see that he would move to the right, or because this is the ideal direction to move if you are in that particular state. And you can see starting from our initial state, we're simply going to follow the maze along in the shortest available path and reach our goal. Here is an example of a value function. So in this, the numbers are going to represent the value of each state. So it's really valuable to be right next to our goal, but not so valuable to be at the start, and really awful to be stuck down in the bottom left corner of this maze here. So we want to move in a direction where our future actions are going to have a higher reward, so we're going to want to move towards our goal. In the last case, we might have a model. So maybe our agent understands that this is the general route that it should go, but it's important to understand that the model may be imperfect. So in this model, there are a couple wrong moves in there. Maybe it takes a right turn right at the start of this maze, and that's going to be an incorrect model, but in general, this is going to make it to our goal. So these are the 3 different ways that an agent could solve this maze. It could use policy, it could use a value function, and it could use a model, although it may be imperfect. Or it could use a combination of these 3. So let's move on, and we're going to talk about learning and planning a little bit, and how our agent actually can use reinforcement learning or use planning and beliefs about its environment to move forward. So these are the 2 aspects of sequential decision making, and reinforcement again is primarily concerned with sequential decision making. The first is reinforcement learning, second planning. So in reinforcement learning, the environment is initially unknown. This is if you don't have a model, you don't know what you're interacting with. Maybe you're playing an Atari game and you don't know the rules. However, the agent is going to interact with the environment, so we start playing the game and we get feedback from that. Maybe we won, maybe we lost, and generally we're going to improve our policy as we continue to learn. So we're going to get better and better at playing the game, even though we weren't explicitly told the rules. The alternative to that is planning, where the model of the environment would be known, and this could be maybe fully observable or partially observable. So we may know the entirety of the model, we know all the rules and all the best actions. Maybe we only know some of the rules and some of the actions. And then the agent is going to perform computations with its model and use those computations to improve its policy. So this is going to be when our agent is making predictions about the future or forming beliefs about its environment so that it can choose an action that it thinks is going to maximize its reward beforehand. This is very much so planning out its attack instead of just learning by trial and error, such as in the more strict reinforcement learning. So each algorithm is going to use a combination of these two approaches. Most of them are going to do some planning as well as some trial and error. But overall, the goal is going to be to form that policy that results in our maximum reward. So a quick summary of reinforcement learning, because this was just a very brief introduction and very quick. In reinforcement learning, our goal is to learn the best policy or learn the best sequence of actions that maximizes our reward, and our reward is going to be defined in different ways in different examples. And some elements of reinforcement learning, we have the agent, which is the decision maker, and the agent is actually the one performing the learning. We have the environment that the agent interacts with, and this is going to be the current state or space that it's in, state being the current environment, the environment being maybe the rules of the game or the maze that the agent is in. We have actions, which are possible moves by the agent, and we have reward, which is the feedback on our sequence of action, often coming only at the end of the game. So this is reinforcement learning in a nutshell. Again, we are going to take a look at a reinforcement learning example using the OpenAI Gym environment in Python in our final project. So we're going to help you understand this better by getting your hands dirty and actually programming a deep learning reinforcement algorithm. So stay tuned for that. That's going to be exciting and really help reinforce, pun intended, some of these concepts. Thanks for listening.